Good morning, students. In the last class, we discussed about the dielectrics, right? So that is polar dielectrics and non-polar dielectrics, right? So today we will start with the new topic, that is capacitor and capacitance, right? So what is capacitor? First, we will discuss on the capacitor, and later we move on to the capacitance, right? So what is capacitor? Right? So capacitor is a device which stores the charges. So that one we call as a capacitor, or we can say capacitor is a system of two conductors separated by an insulating medium or dielectric medium. So that one we call as a capacitor, right? So what is capacitor? Capacitor, it is a device which stores charges, right? So what is a capacitor? Capacitor is a device, it stores the charges, right? So if you define the capacitor, it is a system of conductors separated by a dielectric medium or insulating medium, right? So this gives the definition of the capacitor, right? So what is capacitor? Capacitor is a system of conductors separated by a dielectric medium, right? So what is the purpose of capacitor? So capacitor is used to store the charges, right? So conductor may be of any shape or any size, right? So consider two conductors, right? So calling this one as conductor 1, it stores the charges q1, that means the charges on the conductor is q1, and calling this one as conductor 2, the charges on this conductor is q2, right? So these two charges are separated by a small distance, right? So in the study of capacitors, right? So we are considering the charges on the q1, one conductor, that is charges on one conductor we taken as positive, so that one we taken as plus q, and the charges on the another conductor is taken as negative, hence the charges on q2 we taken as minus q. So this overall system of the two conductors we call this one as capacitor, right? So if it stores the charges, means that means the charges on this conductor means it has a potential, right? So that potential we call as V1, and the potential on the conductor 2 we call that one as V2, right? So the potential difference between these two conductors, right? So that one we taken as V is equals to V2 minus V1, right? So when the conductor, these two conductors are connected to the external battery, right? So these two are connected to the external battery, then this stores the charges, right? So when we connected these two conductors to the external battery, then these two stores the charges, right? So these two conductors we taken one as positive and another one as negative, then there is an electric field in between the two conductors, that is from positive charge to the negative charge, right? So as the charges are linearly distributed on the surface of the conductor, then electric field is uniformly distributed in between the two conductors, right? So electric field is directly proportional to the charges which are present on the conductor, right? So if we have more number of charges, then the electric field is increased. That means if we increases the charges, then electric field is also increases. Hence we written electric field is directly proportional to the charge Q, right? So now the potential difference, as we applied these two conductors which are connected to the external source, that is the battery, right? So here we have the potential difference V, right? So potential difference means that is we are bringing the work done in bringing the unit test charge from one conductor to the another conductor opposite to the direction of the electric field, right? So that one we call as the work done per unit charge, right? So that we call as the potential V, right? So this potential is directly proportional to the charge Q, right? So what is potential? The work done in bringing the unit test charge from one conductor to the another conductor opposite to the direction of the electric field, right? So that one we call as the potential. So that potential is also proportional to the Q, right? So from this relation we can write Q by V is equals to constant, right? So this constant we name as capacitance and it is denoted C, right? So capacitance is a property, that is inner property of the capacitor, and it is defined as the ratio of a charge per unit volt. It is the ratio of the charge of the voltage, right? So that constant we call as capacitance, and this capacitance is independent of Q or V, right? So this capacitance C, the value of C is independent of these two values, right? So here C is not any related with Q and V. The ratio of Q and V is independent of C, right? So then on what factors this capacitance of a capacitor depends, right? So the capacitance of a capacitor depends So very important for 2 marks. Several times they ask this. So on what factor capacitance of a capacitor depends, right? So the first factor is the geometrical shape of the conductor, right? Geometrical shape of the conductor. That means size and shape of the conductor, right? So on what factor this capacitance depends on the size and shape, right? So that means area, right? So it depends on the area and how much distance separation between the two conductors, right? So next one is distance of separation between two conductors, right? So this one is the second point. Next, and the third point is dielectric medium between the conductors. So dielectric medium is nothing but the insulating medium. So very important for 3 marks or 2 marks. Several times they ask the factors, on what factors the capacitance of a capacitor depends, right? So what is capacitor? So capacitor is a device which stores the charges, right? So the general construction of the capacitor is two conductors which are separated by a small distance, and these two conductors are connected to the external battery. So there is a potential difference between these two conductors. So as the one conductor charges on the one conductor is positive and the charges on the another conductor will be taken as negative, so there is an existence of the electric field. So this is directly relates with the charges. So if we increases the charges, the electric field lines also increases. That means Q is directly proportional to E. And the work done in bringing the unit charge from one conductor to the another opposite to the direction of electric field. So that one we call as the potential. So work done per unit charge, we call that one as potential. That potential is also proportional to the Q, and the ratio of Q by V we call that one as a capacitance, and this capacitance is independent of both Q and V, the ratio of Q and V, right? So the factors on which it depends, that is geometrical shape of the conductor, that is the shape and size of the conductor. Next, the distance of separation between the two conductors. Next, the dielectric medium between the conductors. So if you place any dielectric medium or insulating medium in between these two conductors, so then also the capacitance varies, right? So this is about the capacitance, right? So next we have the relation C is equals to Q by V, and it has the unit, right? So SI unit for capacitance is farad. So calling this one as F. So F gives the unit of the capacitance, right? So capacitance unit is farad, and 1 farad, that is equals to 1 coulomb per volt, right? So SI unit for charge is coulomb and SI unit for voltage is V. That is potential difference is V, right? So we call that one as 1 farad is equals to 1 coulomb per volt, right? So next, parallel plate capacitor. So 3 marks, very important derivation. Right? Parallel plate capacitor. So in the name itself it says the parallel plate. So we are considering two conductors which are parallel to one another, right? So this one calling as conductor 1 and conductor 2. So sigma is the surface charge density on both the conductors. So plus Q, here we have minus Q. So when we charge the conductor 1 positive, right? So due to the induction, the negative charges will be stored on the conductor 2. So as the charges are linearly distributed or uniformly distributed on the conductor, so hence we have the electric field, that is uniform electric field E, that is from plus charge to the minus charge, and A is the area of the conductor. So this one is the first conductor, 2 conductor, right? So both having the same area, that is A, right? So now these two conductors are connected to the external battery, right? So this one is the potential plus and minus, right? So from the properties, that is results on the conductor, so we have one relation, that is electric field on the surface of a charged conductor is E is equals to sigma by epsilon. So in the last class we discussed the results of the conductors. That means the result we have discussed in the last class is the electric field on the surface of any charged conductor. We have the relation E is equals to sigma by epsilon naught. So here we are considering one plate, right? So one conductor, so we call this one as plate, right? So here we have the charge density sigma. So we know the charge density distance between the two capacitors, right? So where V is the distance between the two capacitors. Now substitute here V is equals to E, that is Q epsilon naught A into D, right? Calling this one as equation 2. So from the definition of capacitance, C is equals to Q divided by V, right? So that is from the definition of the capacitance, C is equals to Q by V. So here we have the value for V, right? So C is equals to Q divided by QD divided by epsilon naught A. That is from equation 2, right? So here plus Q, here plus Q get cancels, so we get C is equals to epsilon naught A divided by D. So this gives the relation for the capacitance of a parallel plate capacitor, right? So very important relation for 3 marks. So give the expression for a capacitance of a parallel plate capacitor means. So first consider two conductors so of equal area separated by a small distance d. So when sigma is the surface charge density on the conductor, so plus sigma represents plus charges on the conductor 1 and minus sigma represent minus q charges on the conductor 2, right? So now we connected these two parallel plates connected to the external source, that is V. So from the property, that is from the result, that is electrostatic field due to the conductor, from that relation we find E is equals to sigma by epsilon naught, right? So that is on the surface of any conductor the electric field E is equals to sigma by epsilon naught, and we know the surface charge density sigma is equals to Q divided by A. Now substituting sigma in the equation E, so we get E is equals to Q by epsilon naught A. So from the potential, the relation between the potential and to that of the electric field, V is equals to E into D. So we substitute the value of E. So we get the potential V is equals to Q divided by epsilon naught A by D. Right? So from the definition of capacitance, C is equals to Q by V. So substituting the value of V here, Q D divided by epsilon naught A. So Q get cancelled. So capacitance is equals to epsilon naught A divided by D. So here also on what factors the capacitance depends means the dielectric medium. So that is epsilon naught permittivity, area and the distance between the plates. So this gives the geometrical representation, that is geometrical shape of the conductor, right? So capacitance is proportional to the area. If we increase the area of a conductor, then capacitance increases. So if we decrease the distance between the conductors, then also the capacitance increases, right? So this one is the important relation, that is C is equals to epsilon naught A by D, right? So next, when a dielectric medium is inserted in between the plates, right? That means when the insulating material, initially we have E here, right? So take on that one as E naught. So electric field E naught, that is due to the conductor 1 and 2, because initially it has a charges, that is plus Q and minus Q, right? So now this dielectric is introduced. So when dielectric is introduced in between the two conductors, so in the last class we discussed the dielectrics contains the polar or non-polar molecules. So when it is inserted in between the conductors or in between the electric field, so there is a linear arrangement of the charges, right? So polarization takes place in the dielectrics. So that is as we discussed in the previous class, right? So when an dielectric is introduced in between the electric field, that is external electric field. So here the electric field is E naught, that is by the charges which are on the conductor 1 and conductor 2, right? So now here polarization takes place, and in here in between the electric field we have one more electric field, that one is due to the polarization, that is from plus charge to the minus charge, right? So now here sigma p is the charge density, right? So surface charge density in the dielectrics we denoted by sigma p, that is due to the polarization. So here we have minus, so hence we have minus sigma p. Here we have plus, so hence we taken here plus sigma p, right? So now considering overall this one, so the total net charge density on the conductor 1 is sigma minus sigma p, right? So this minus sigma p is due to the dielectrics, right? So here on the surface charge density on the second conductor is minus sigma plus sigma p, right? So where sigma p is the surface charge density due to the dielectrics, right? So here sigma is the charge density on the conductor. Initially we have the sigma, right? So the electric field we applied here is E naught, right? So initially in the air medium we taken that one as E naught here, and potential V naught is equals to E naught into D. So that is in air medium, right? So next, capacitance C is equal, that is C naught is equals to epsilon naught A divided by D, right? So this is when in the air medium. This is in the air medium, right? So next, when dielectrics is introduced, right? So when dielectric is introduced in between the two conductors, so here the net charge density on a conductor, net charge density on the conductor is sigma minus sigma p. So this gives the net charge density on first conductor, right? So if we take and compare conductor, means we can write plus or minus sigma p, right? So we can take anyone. So here the net charge I will take here on the first conductor. So the net charge density on the first conductor is sigma minus sigma p, right? So this is proportional to sigma p is proportional to the surface charge density sigma, right? So now if we remove the constant sigma minus sigma p, that is equals to sigma divided by k, right? So now substitute this to the electric field, right? So same derivation if we repeat, right? So electric field E is equals to, when an external electric field E, right? So E is equals to sigma minus sigma P, that is in place of sigma, right? Divided by epsilon naught, right? So here we have sigma minus sigma P, that is equals to sigma by K, right? So E is equals to sigma divided by K epsilon naught, right? So again we know sigma value is Q divided by K epsilon naught A, right? So again by the potential difference, V is equals to E into D, that is V is equals to E, we have Q divided by K A epsilon naught into D, right? So now again by the capacitance, C is equals to Q divided by V, right? So C is equals to Q divided by Q D K A epsilon naught. So Q get cancelled. So capacitance C is equals to K A K epsilon naught A by D. This is when dielectrics is introduced. So without dielectrics, we taken C naught is equals to epsilon naught A by D. When the dielectric is introduced, then we get the relation C is equals to K epsilon naught A by D. So in the last chapter also we discussed the dielectric medium K is equals to 1 for air medium, right? So hence here we get K value is equals to 1, right? So this is in air medium, right? So K is equals to infinity for metals, right? So now by this relation we can state that on what factors the capacitance of a capacitor depends, means so C depends on area, C depends on the dielectric medium K, and C is inversely proportional to the distance between the conductors, right? So how we increase the capacitance of a capacitor means by increasing the area of the plate. So if we increase the area of the plates, then capacitance increases. Next, if we increases the dielectric medium, then also the capacitance of a capacitor increases, right? So next, if we decreases the distance between the two plates, then the capacitance of a capacitor increases. So they ask this one also for 3 marks. Either they ask how or on what factor. So if they ask how capacitance of a capacitor increases means we need to write if we C is directly proportional to, or if we increase the area of the capacitor and dielectric medium between the plates, and if we decrease the distance between the conductors, then the capacitance of a capacitor increases. So if they only ask the on what factor capacitance of a capacitor depends means on area of the plate. Next, dielectric medium and distance between the plates, right? So this is about the capacitors and capacitance. So this one is very important formula. So in general we can take C is equals to K epsilon naught A by D. So this one is the basic formula, right? So when dielectric, if they given in a air medium, we can take K is equals to 1, then C is equals to epsilon naught A by D, right? So from these two relations, we can write C divided by C naught, that is equals to K, or C is equals to K times of C naught, where C naught is initial capacitance, right? So from these two relations, from 1 and 2. So from 2 we can write C by C naught. This C is the capacitance in dielectric medium and C naught is the capacitance in air medium. So that gives what? Dielectric constant, that is K. When K is a constant, that constant we call as the dielectric constant. So that one we already discussed in our last chapter, right? So from this we can say the dielectric medium increases, then the capacitance of a capacitor increases, right? So capacitance of a capacitor increases means the amount of charges which are stored on this capacitor increases, right? So now so at the edges, the electric field lines are bending, right? So from positive charge to the negative charge, and that effect we call as the fringing effect. So the fringing effect we can decrease. So this effect we can decrease by decreasing the plates, right? So if we decreasing the plates compared to that of the area of the plate, then this fringing effect we can remove or reduce, right? So next, so next one is the electric field. Here the electric field, up to what extent the capacitor of a capacitance stores the charges, right? So the electric field is about 3 into 10 to the power of 6 volt per meter, right? So it can store up to this electric field. When we apply this much of the electric field, then the maximum storage of the charges on the capacitor. So if the distance between these plates is kept at 1 centimeter, then the potential applied between these two plates is of about, that is 3 into 10 to the power of 4 volt, right? So up to these values, so we can store the charges in the capacitor, right? So this is about the capacitor and capacitance. So simply what is capacitor means, it stores the charges in between the conductors, right? So that property we call as a capacitance, right? So unit of capacitance is farad, and we have the main relation C is equals to epsilon naught A divided by D, right? So in the next class we will discuss some combinations of capacitor, right? So when capacitors are connected in series and in parallel, and also we discussed energy stored in capacitor, right? By this we can complete the chapter, right? Thank you. Doubts?